As far as we understand, time moves in only one direction, forward. But what if it were possible to loop back and witness an earlier point in the universe's timeline? This leads to one of the most famous paradoxes in theoretical physics. Imagine traveling to the past and preventing your grandfather from growing up. If he never had children, then your parents wouldn't exist, which means you wouldn't exist either. But if you were never born, then how could you have traveled back in time to alter history in the first place? That's the grandfather paradox. One common explanation is that traveling to the past doesn't actually change your own timeline, but creates a parallel reality, a separate branch of events. In this alternate version of history, your actions influence the future of that specific timeline, but they don't affect the past that led to your own existence. While this avoids contradiction, it also sidesteps the paradox rather than resolving it. A more intriguing perspective assumes that any changes made in the past do affect the present and future in a continuous loop. If you prevent your grandfather's existence, then you cease to exist, which means you never went back to alter history, allowing your grandfather to live. This cycle repeats infinitely, forming two interwoven histories happening simultaneously. Is such a paradoxical timeline even possible? While we don't know if time travel works this way, quantum mechanics offers a fascinating analogy. At the subatomic level, particles can exist in multiple states at once through quantum superposition, a phenomenon seen in the double-slit experiment and the fusion reactions powering stars. If the universe functioned similarly, it could theoretically exist in a superposition of two states. Your grandfather survives, so you are born and travel back in time. Your grandfather does not survive, so you are never born and never travel back. This ongoing cycle suggests that such a paradox might not be an inconsistency at all, but rather a self-sustaining system within quantum physics. Alternatively, some approaches in mathematical physics, like Markov chains, suggest that a paradox-free resolution exists through equilibrium states, though exploring that in detail is another discussion. Of course, none of these interpretations prove that closed time loops are possible. In fact, certain ideas from complexity theory suggest that time loops may be fundamentally impossible. Ultimately, what we often see as a paradox may simply be a limitation in our way of thinking. The real mystery isn't just time travel itself, it's how our minds can conceive of paradoxes like the grandfather paradox, but struggle to fully grasp the nature of time itself. This version keeps the original ideas intact, while making it more original and polished. Let me know if you want any tweaks. Blast off.